Hi everyone, so in this video we are going to see the problem based on binary parallel adder. So we have already seen the problems based on delay in full adders and half adders. So I hope you have seen that, then only you should come here. And just like the previous video, this also requires your high attention. So just pay your full attention, then only you will be able to understand. So here we will see 4 types of problem. This is type 1, we will see type 2, type 3 and type 4 with a lot of examples. So let's start with the first question. So 4-bit binary parallel adder is there, which is made using 4 full adders. For each full adder, the sum is produced after 10 nanosecond of delay and carry after 15 nanosecond of delay. You need to find the time when you receive the stable output. The complete output is stable. So in binary parallel adder, if you have studied it, there are unstable state as well, because these states A3, B3, A2, B2, A1, B1, A0, B0, all these bits will be applied at t equals to 0. All these bits will be applied at t equals to 0. So initially there is no carry here, there is 0. Initially 0, like before t less than 0. For t less than 0, there was no carry here, there was no carry here, there was no carry here. So now this guy will perform the calculation. This full adder will perform the calculation that one of my bit is this, one of my bit is this, and one of my bit is this. So it will perform the calculation considering A2 plus B2 plus 0. So here you will get the unstable output, because who knows, from the previous stage your carry could be 1. So after that output again can change. So in between there will be unstable states, right? So we need to find when your output is stable. So all these inputs are stable at t equals to 0. So if I write my stable output, this is what I am writing my stable output. Here I will write my stable output. So initial C0 I am taking as 0, because it is given initial C0 is 0. So this will generate some as 0 and will generate a carry. This is stable output. So now the output is given as A1 plus B1 plus C1. So it will generate S1 and carry. Now output is generated as C2 plus A2 plus B2, S2 and carry. Output is generated considering C3 plus A3 plus B3, S3 and carry. Okay, so this is the final output. So when we will receive this stable output, this is what they are asking. So now they are saying, now the operation will start at t equals to 0. Now they are saying that sum is produced after 10 nanosecond of delay. So this is showing my sum. Okay, this is my sum S0, S1, S2 and S3, and this is showing my carry C0, C1, C0, C1, C2. Oh no, sorry. This is C1, C2, C3. Really sorry. C1, C2, C1, C2, C3, and this is your final carry C4. Okay. Now all these bits are applied at t equals to 0. The sum is produced after 10 nanosecond of delay. So these guys will produce the sum after 10 nanosecond of delay. So to travel from here to here, it will take 10 nanosecond of delay. So this will be stable after 10 nanosecond, right? This guy is stable at t equals to 0 nanosecond only. This guy is also stable at t equals to 0 nanosecond, and this guy is also stable at t equals to 0 nanosecond. What about this guy? Now the stability of this guy depends on this output, right? And now this output is generated after 15 nanosecond of delay. So when A and B were there ready, now this full adder was ready to give the output, because this input is stable, this input is stable, this input is stable. So this full adder is ready to give the output. So it will take 15 nanosecond of time and this will be stable. So now what about this full adder? So this full adder will say that A1 is stable, B1 is stable at t equals to 0 only, but my third input is not stable at t equals to 0. So I cannot produce the output at t equals to 0. So I will have to wait. So full adder will wait for this guy, because full adder will say that at my input A is stable, A1 is stable, B1 is stable at t equals to 0 only, but I cannot give the output because I have to wait for this guy, and this guy will be stable after 15 nanosecond. So after how much time it will generate the output? 15 nanosecond. For the sum it will take 10 nanosecond more, so 25. And for carry it will take 15 nanosecond more, so 30 nanosecond. Here it will generate the carry after 30 nanosecond. Now what this full adder will say, that my inputs are stable at t equals to 0 only, but this guy became stable after 30 nanosecond. So I can start working after 30 nanosecond. So 30 nanosecond plus 10 nanosecond it will take for reducing your sum, and 15 nanosecond, 13 plus 15, 30 plus 15. So at 45 nanosecond it will produce your what do we say, this carry. Now this guy will say that I was able to perform the addition at t equals to 0 nanosecond if this guy was stable, but this guy is stable at 45 nanosecond. So now I will take 55 10. Now I will start working at 45 nanosecond. To produce the sum I will take 10 nanosecond more, and to produce the carry I will take 15 nanosecond more. So your final carry is produced at 60 nanosecond and sum is produced at 55 nanosecond. So what will be that maximum delay? Maximum delay to receive the stable output. Stable output means my S3, S2, S1 and S0, this should be stable, and C4 should also be stable. This is what I mean by stable output. That my S0, S1, S2 and S3, these should be stable, and C4 should also be stable. So this is what I mean by stable output. So my S3, S2, S1 and S0, they were stable latest by 55 nanosecond, and my C4 was stable at 60 nanosecond. So what is my maximum delay? 60 nanosecond. Say yes or no. This is the first kind of problem that we have covered. So my sum was stable at 55 nanosecond, but final carry, I will say final carry. Okay, final carry, because there were in between there were many carries, but final carry we are talking about was stable at 60 nanosecond. So maximum delay in receiving stable output, what is that? 60 nanosecond. Okay, now let's solve this particular problem considering that there are n bit parallelly added. It is n bit parallelly added. Okay, they are n bit parallelly added. So how will I solve it? So look, all these are stable at t equals to 0. So we'll change the color. So this guy will be stable after ts time. I am calling the sum will be stable after ts time and carry will be stable after tc time. Okay. No, final, they are not final. So I am calling this delay as ts, this delay as ts, and this delay as tc. Okay. So it is applied at t equals to 0. So at t equals to 0 it started working, it will give output at ts. This will give output at tc, right? Now this guy will start working at tc. This guy will start working at tc. So it will give this output after tc plus ts and will give this output at 2 tc, right? Now this guy will start working at 2 tc. So if this guy started working at 2 tc, now it will give output of sum. It will take ts time more. So sum output will be given as 2 tc plus ts, because to produce the sum it will take ts time more, and to produce the carry it will take tc time more. So it will give after 3 tc. So now 3 tc is fed here. Now this guy will start working at 3 tc. So it will give output of sum after 3 tc plus ts, right? And it will give the carry output at 4 tc. Say yes or no. Did you understand this point? Again I am repeating. At t equals to 0 it was stable. So ts will be this sum will be received after ts time, because this circuit started working at t equals to 0. So this will be received, but carry will be received after tc time. So this tc is going here. Now this guy will start working at tc. So it will give you sum after tc plus ts. Tc plus the time taken for the sum to get out. So that is tc plus ts. And for the carry, tc plus another tc, 2 tc, right? Because carry will take tc time. So tc plus tc 2 tc. Now this guy will start working at 2 tc. For carry it will take 2 tc plus ts time. For sum it will take 2 tc plus ts time. For carry it will take 2 tc plus tc time. So this guy will be starting working at 3 tc. For sum it will take 3 tc plus ts time. For carry it will take 4 tc. So what did you understand? For 4 bit binary parallel adder, your carry is being stable at 4 tc and your sum is being stable at 3 tc plus ts. 3 tc plus ts. Try visualizing this circuit in your mind. Close your eyes and try visualizing it. That sir, first tc, after tc it would come up, then sum will come up after ts and tc would go there. So this guy will start working at tc. So this will take tc plus ts and 2 tc. This guy will start working at 2 tc. So it will take 2 tc plus ts, and this guy will start working at 3 tc. So it will take 3 tc plus ts and 4 ts. So for n, how much it will take? So sum will be stable after n minus 1 tc plus ts, n minus 1 tc plus ts, and carry will be stable at n tc. Can I write this as n minus 1 tc plus TS. Look, if they are asking what is the maximum time to receive stable output, then you should pick the maximum value of this. Here I picked this value, 60 nanosecond. Why did I pick this 60 nanosecond? Because this was more. Here I don't know the value of TS and TC. I don't know these values. So I don't know which one will be more. So what I can do, I wrote NTC as n minus 1 TC plus TS. So these two are same, right? Let's just say n minus 1 TC is 5. Now TS is 3 and okay, n minus 1 TC plus, sorry, this would be TC only. N minus 1 TC plus TC. And TC can be written as n minus 1 TC plus TC. And this TC is 4. So which one is the maximum? 9. So this one will be your answer. So can I write it in this manner? That your delay will be n minus 1 TC plus maximum of TC plus TS. Sorry, TC comma TS. Maximum of TC comma TS. If this TS was 5, then you would have picked this answer, right? So your answer would be n minus 1 TC plus TS. Are you getting this point? How did I write it? N minus 1 TC plus TC. I just wrote NTC as n minus 1 TC plus TC. Then I got to know that these two are same. If I need to make a formula that what will be the maximum time taken to receive the stable output, so that would be n minus 1 TC plus maximum of TC plus TS. You don't need to remember it, but what if it is there in some of the option? Like in the option only, they are framing the problem like this, that what will be the maximum. This direct question is coming and ABCD options are there. N minus 1 TS plus maximum of TC TS, n minus 1 TC plus maximum of. So there it will be used. Otherwise, if the questions are coming like this, the same question is there. A 16-bit binary parallel adder is made using 16 full adder. For each full adder, the sum and carry both are produced after 10 nanoseconds of delay. Then find the time taken to receive the stable output. So what about carry? So in the mind only I will think, wait a second. So in the mind only I will think, what I will think? That carry will be generated here after TC. Then this guy will start working after 2 TC. So this will receive, this guy will start working at TC. So this will be received after 2 TC. So second output is being received after 2 TC. That means 16th output will be received after 16 TC. That's it. And what about sum? So for sum I will think that first will be received at TS. But second guy, TC will go, it will generate at TC plus TS. Third guy, 2 TC will go, it will generate at 2 TC plus TS. So third guy is giving 2 TC plus TS. So nth guy will give, or 15th guy will, 16th guy will give at 15 TC plus TS. So that would be my answer. Now TC and TS both values are same only. So 160 nanosecond, and here also 160 nanosecond you will get. So answer is maximum delay is 160 nanosecond. Okay, so the block diagram should be clear in your mind. Again I am repeating, again and again I will explain this concept very slowly because it is very important and it is not taught in that good manner. So we are going to see this. Okay, so first after 10 nanosecond data is received and 15 nanosecond and 10 nanosecond only the carry was received. So carry went here, this guy started working at 10 nanosecond. So 10 plus 10 after 20 nanosecond sum will be received, and 10 plus 10 after 20 nanosecond carry will be received. So next guy will start working. So in that manner it will keep on going. So it will be added up. So you do not need to solve like each stage, but you will see a pattern there. The TC time is being added, right? You will see a pattern. Now I will frame the question more interesting. These kind of question is not asked and can be asked. Okay. Now it is 8-bit binary parallel adder is made, but all the full adders are different now. Full adder 1, 3, 5, 7. 1, 3, 5, 7. These have the sum delay of 30 nanosecond and carry delay of 10 nanosecond, and the rest of the guys will have 20 and 30. You can solve it on your own, then match your answer. Okay. So in the examination, I am not going to make this structure, okay, this beautiful structure, nothing like that. I know all input will be coming at t equals to 0. So why to make these arrows? It will just waste my time. And this will also come at t equals to 0. So I know that. I am just going to write the timings. So both input are coming at 0. So this guy will start working at t equals to 0 only. This guy will start working at t equals to 0. So if this guy has started working at t equals to 0, then it will, what about full adder 1? So it will give the sum after 20 nanosecond and carry delay after 30 nanosecond. So now this guy will start working at 30 nanosecond. This guy started working at 0 nanosecond. This guy started working at 30 nanosecond. So it will give the sum after 30 plus 30 60 nanosecond, because here sum is taking 30 seconds and carry is taking 10 nanosecond only. So here carry is 10, here carry is 30. So this will give output after 14 nanosecond. Now this carry is being fed to this. So here input was stable at t equals to 0 only, and this carry is being fed here. So that means this circuit will be in position to give output after 14 nanosecond only. It will not wait till 60 nanosecond. Are you getting this point? Here you received this output at 14 nanosecond, right? So and this is being fed here, that you know. So this guy will be in position to give output at 14 nanosecond only, because these are stable, these are already stable, and this guy became stable after 14 nanosecond. So now this guy will say that now I have the capability of giving the output. So this guy will start working at 14 nanosecond only. And what is the sum delay for this? That is 20. So this sum will be stable at 60 nanosecond. And what about the carry? Carry will be stable at 70 nanosecond. So this guy will start working at 70 nanosecond. So what about full adder 3? So full adder 3 will give the delay after 30 nanosecond, and carry delay it will give quickly 80 nanosecond. Now this 80 nanosecond is fed here. So this guy will be in position to give the output after 80 nanosecond. So 80 nanosecond, this is full adder 4. So sum will be given after 20 and the carry will be 110. So this guy will start working at 110 nano. So what about full adder 5? So full adder 5 will give the sum after some time, but carry it can give in only 10 nanosecond. So this guy will be in position to give the output at 120 nanosecond. So full adder 6, for full adder 6 the sum will be received at 140 nano, but carry will be received at 150 nano. So this 150 nano goes here, right? So if this 150 nano goes here, so this guy full adder 7 will be giving the sum after 30 nanosecond, that means 180, and it will give the full adder 7 and will give the carry after 10 nanosecond, so 160 nanosecond. So final carry is received at 160 nanosecond, and final sum. So these sum were stable. This was stable at 20, this was 60, 100, 140, and then 180. So this guy was stable at 180 nanosecond. So final sum is stable at 180 nanosecond. So this is the answer, maximum delay. So these kind of questions are not asked every time they have framed the same kind of full adder. But what if they change the full adder? So no formula will work here. You need to know the concept. Like every time I have seen people solving these kind of questions with formula. N minus 1 Tc plus maximum of Tc plus Ts, maximum of Tc and Ts. But what is the meaning of that? This is the meaning of that these kind of questions can also come out. Okay. So this is done about our pattern 1, type 1 or pattern 1 you can say. Now we will take a pause and we will solve the questions of pattern 2. Okay. So I will take a pause and then we will solve the questions of pattern 2. So now this is our type 2. So a 4-bit binary parallel adder is made using 4 full adders. Okay. Each full adder is made using 2 half adder and 1 OR gate. Each half adder is made using XOR gate and AND gate. Delay of XOR gate is 30 nanosecond, AND gate is 20 nanosecond, OR gate is 10 nanosecond. Find the time in getting the stable output of binary parallel adder. Now 50% of the student will think that I can solve this question, right? Because full adder is made using half adder. I have studied the analysis of full adder already. So what I will do, I will generate the sum and carry. I will see the time in which sum and carry are stable, and then I can solve by the previous analysis, right? So this is what you guys are thinking. So let's solve by that. So 30, 20 and 10. So this is the internal structure, half adder and this OR gate. So when your sum will be generated, so sum will depend here. So this guy is stable at t equals to 0, but this guy will be stable at t equals to 30 nanosecond. So 30 plus 30, 60 nanosecond. So sum will be stable at 60 nanosecond. And what about this carry? So this carry will depend on here. So this guy is stable at 20 nanosecond, right? What about this guy? So in this guy is stable at 30 nanosecond, and this carry is stable at 0 nanosecond only. So 30 and 0, but this guy will have to wait for this guy. So 30 plus 20, here 15 nanosecond. So 50 nanosecond, this guy is stable at 50 nanosecond, this guy is stable at 20 nanosecond. So 50 plus 10, 60 nanosecond. So you are saying that my sum is also stable at 60 nanosecond and carry is also stable at 60 nanosecond. So it is 4-bit binary parallel adder. So what will be the time taken for the sum to be stable? That would be 4-bit binary parallel adder. So 60 nanosecond will go, 60 nanosecond will go. So 3 into 60 plus TS, that is 60 only. So answer would be 240 nanosecond here. Wait a minute, I am not saying this is the correct answer. This is how you would be solving it. Okay, and for here it would be NTC. The carry will be stable after NTC only. TC plus TC plus TC. For some TC plus TS, 2TC plus TS, 3TC plus TS, 4TC plus TS. So in that manner 3TC plus TS. For this it is 4TC. So you are getting 240 nanosecond. So this is the maximum delay you are thinking, and this will be there in the option, and this is wrong. Now why is that wrong? Your full adder is made using half adder. Okay. What will be the complete equivalent circuit? Try making it. You are not going to make it in the examination. I will tell you the method how to solve it, but try making it once. What will be the complete circuitry? I am asking you to make binary parallel adder using full adders, but there each full adder is made using half adders. So try making the circuit. You can make it. So this is how the circuit will look like, right? A node, B node is there, half adder is there. It will generate the carry. In between the carry, this carry I am talking about. This guy I am talking about. This is your question mark. So this will be your question mark. Sorry, this will be your question mark. Sorry, this guy. And now this will be A XOR B. This I am calling sum. This I am calling carry. Okay. So this will generate some carry. This will be fed here. And for this I am calling sum. This I am calling as carry. So both of the carries are being owed. Here you can see carry of this guy and carry of this guy. Both are being owed. Carry of this guy and carry of this guy. So carry of first half adder and carry of second half adder is being owed, and now this carry will be fed to the next stage. This is the final carry, right? This is Ci plus 1. This is Ci plus 1, or you can say for here it would be C1. So this C1 will be fed here now, and then operation will keep on going. This will be your C2 and this C2 will be fed here, right? This will be your S0. This will generate S1 here. For S1 XOR of this and then again XOR, right? C2 and this will be your S2. This will generate next carry, that is C3. This C3 is being fed here, so it will generate S4 and final carry C4. This is what is happening. Okay. Now tell me one thing. If you analyze only a half adder, so only for half adder, both of the half adders are same only, no? So for half adder, what is your TS? 30 nanosecond. And what is your T carry? This will be your carry and this will be your sum, right? So for half adder, what will be your carry? 20 nanosecond. So if I start here, so all these inputs, why I have written A naught B naught, it would be A1 B1, sorry, A2 B2 and E3 B3, A3 B3. Now all these guys are stable at t equals to 0. All these guys are stable at t equals to 0. Right? All these guys are stable at t equals to 0. Now, to generate the sum, how much time it will take? 30 nanoseconds. So here I am already writing that to generate the sum I am taking 30 nanosecond time to generate a carry out of half adder. For half adder, and to generate a carry I am taking 20 nanosecond. So these guys will start working. This will be generated after 30 nanosecond and this will be generated after 20 nanosecond. But this guy is not stable yet. Now 30 plus this will take 30 more. So this guy will be stable at 60 nanosecond, and for carry it will take 20 more. So this guy will be stable at 50 nanosecond. Now both guys will go 20 and 50. So this guy will be waiting for this guy. So 20 plus OR gate is having 10 nanosecond delay. So this guy will be stable at 60 nanosecond. Now this guy will be stable at 60 nanosecond. Right? Now tell me one thing. These two guys were stable at t equals to 0 only, no? These two were stable at t equals to 0. So for half adder you need only two inputs and both are stable at t equals to 0. That means this guy started working at t equals to 0 only. And if this guy started working at t equals to 0, so this input is already stable. This input TS, this will take 30 nanosecond time to be stable. What I mean to say is that this guy started working at t equals to 0. So this will be stable at 30 nanosecond. So this guy will be waiting for this guy to generate this final output. This guy will be waiting for this guy to generate this final output. So 60 plus 30, it will take 90 nanoseconds to come out. Say yes or no? 60 plus to generate the sum, it will take 30 nanoseconds more. So 60 plus 30, it will take 90 nanoseconds to come out. To here to generate carry, it will take 30 plus 20, 50 nanoseconds. What about this guy? When this guy was stable? Tell me when this guy was stable. So this guy started working at t equals to 0. So to generate the carry, you need 20 nanoseconds. So this guy was stable at 20 nanoseconds. This guy was waiting for him. So it came at 50 nanoseconds. So 50 nanoseconds plus 10. So this will be stable at 60 nanoseconds only. Yes or no? This carry was stable at 60 nanoseconds. This was also stable at 60 nanoseconds and this was also stable at 60 nanoseconds. Why that happened? Because this was already working. Why did not we consider this thing in the previous problem, in the previous pattern, in these patterns? Because here it was given as a black box. Full adder completely was given as a black box, and it meant to say that for each full adder, the sum and carry will be stable after 10 nanosecond, or in the previous problem it was 10 and 15. So internal structure was not given. So here what we meant is that this full adder will be working, when all three input will be stable. This full adder would be working when all three input are stable. But when they are giving the internal structure, we know that one of the half adder in the internal structure itself will start working before waiting for this carry. So this guy was not waiting for this carry. This guy was waiting, but this guy was not even waiting, right? So it started working and gave the output. In the examination, we are not going to draw this circuit. I will tell you how to solve the problem in the examination. So this guy was waiting. So wait a second. This guy came at 16 nanoseconds. Wait a minute. There is an error. So this guy came at 60 nanoseconds. So this guy started working at 60 nanoseconds. So to produce the sum, it will take 30 nanoseconds, and to produce the carry, it will take 20 nanoseconds. So this will be 80 nanoseconds. So both 20 and 80, 10 nanoseconds more, so 90 nanoseconds. Now this guy will be stable at 90 nanoseconds. Okay, sorry for this blunder. This guy started working after 60 nanoseconds, not 30 nanoseconds, because this particular guy was waiting for both of the input to be stable, and input was stable at 60 nanoseconds. So this guy started working at 60 nanoseconds. So to produce the sum, it is taking 30 nanosecond time. To produce the carry, it is taking 20 nanosecond of time. So here 90 nanosecond. Now this input is stable at 90 nanosecond, right? This input is stable at 90 nanosecond. What about this input? This input will be already stable because this guy started working at t equals to 0 only. So this became stable at 30 nanosecond, and this became stable at 20 nanosecond. So these inputs were already stable. Now this input became stable at 90 nanosecond. So this guy will start working at 90 nanosecond. So 90 nanosecond plus 90 nanosecond. For some, it will take 30 nanosecond more. So 90 plus 30, 120 nano. So this will be stable at 120 nanosecond. And what about this? So 120 nano here, and this guy started working at 90 nanosecond. So I will mark it up. This guy started working at 90 nanosecond. This guy started working at 60 nanosecond. So 90 plus for to generate carry, it will take 20 more. So this will be stable at 110 nanosecond. So 110 and 20. So it will pick 110 only. So this will be stable at 120 nanosecond. Right? And what about sum? Sum was stable at 120 nanosecond. So better I should write here 90 plus 120. Now what about this? This is going here. So this guy will start working at 120 nanosecond, and this would have been already stable. So it was not waiting for him. So 120 plus 30, 120 to generate the sum, it will take 30 seconds more. So this will be stable at 150 nanosecond. 150 nanosecond. And what about this? This was already stable. This was already stable. Although the time was 30 nanosecond, this was also already stable. Now at 120 nanosecond, this half adder 3 or 4, sorry, 3, 2 and 1. So now this half adder started working at 120 nanosecond. So 120 nanosecond plus 20 nanosecond to generate here 140, and this has a delay of 10 nano. So this output will be stable at 150 nanosecond. So stable output you are getting at 150 nanoseconds. So maximum delay. What is your maximum delay in this particular problem? that is 150 nanosecond. Okay, so when the internal structure is given, you need to take care of that. Are you getting this point? Whenever internal structure is given, you need to take care of that. In the previous problem, no internal structure was given. Now, how to solve this question in your examination? So, one stage you will draw, okay? One stage you will draw. And the question is saying that XOR gate will take 30 nanosecond, AND gate will take 20 nanosecond, OR gate will take 10 nanosecond. So, on circuit level, I am not drawing, on block level, I am drawing. I know in the half adder internal structure is this. This is the internal structure. I know the internal structure of half adder. That my sum will take XOR delay and my carry will take AND delay. So, this I know, this I will write. Only one stage I am drawing, okay, only one stage I will draw. Now I will get to know that these two will be my input, these two will be stable at t equals to 0 only. So, this will be stable at 30 nanosecond, this is how I will write, and this will be stable at 20 nanosecond. Now, I know one thing, 30 plus 30, this will be stable at 60 nanosecond, and 30 plus 20, this will be stable at 15 nanosecond. Now, which guy is more? This guy is more, so this will be stable at 60 nanosecond. Now, I know one thing, what is that? That this carry is being fed to the next stage. So, this carry is being fed to the next stage here. So, this next stage only here only I am drawing. So, this input has become stable at 60 nanosecond. And now for the next stage, this guy also started working at t equals to 0. For the next stage I am telling, for this second stage. So, in the second stage, this guy also started working at t equals to 0. Say yes or no? Say yes or no? So, this guy would have been already stable for the second stage. This guy would have been already stable, 30 nanosecond, 20 nanosecond. And this guy also would have been already stable. So, you do not need to change these guys. These guys will remain there as it is. Say yes or no? Not changing. So, 30 nanosecond and 60 nanosecond. So, this guy was waiting for this particular guy. So, this guy came at 60 nanosecond. So, they will produce the output after 30 nanosecond more. The sum output I am saying. So, this will be stable at 90 nanosecond. And it will start working at 60 nanosecond. So, 60 nanosecond plus 20 nanosecond. That would be 80 nanosecond. So, this will be stable at 80 nanosecond. So, this guy will be waiting for this guy. So, 80 plus 10. So, this will be stable at 90 nanosecond. So, now this is again fed back. So, this will be 90 nanosecond. No need to care about these guys. Start working at 90 nanosecond only. So, sum will be given at 90 plus 30, 120 nanosecond. 120. Some bit is gone. What about this carry bit? So, 90 plus 20, it will take, I will just mark them up that this is the time where my circuit is working. So, it is working at 90 and this was 60. So, what about the carry bit? 90 plus 20, it will be given at 110 nano. I will make it broad, okay, on a paper I will make it broad, in the examination I am telling. So, 110, so this bit is stable at 110, so it will take 10 more. So, this will be stable at 120 nanosecond. That means now, first stage I have drawn, this was the second stage, this is the third stage, now the fourth stage is coming, that is the final stage. So, this is 120 nanosecond. So, don't care about these guys, 120 nanosecond, 120 plus 30, this will generate final output at 150 nanosecond. So, this is my sum output. What about the carry? 120 plus 20. So, this will be working at 140. It is working at 120, it will take 20 times more. So, this will, you will be getting at 140 and 140 plus 10. So, this will be your final carry. So, this is your final answer, maximum delay. So, this is how I will be solving in the examination. There is no chance of blunder because I know that this is being fed to the next stage and I can analyze the next stage on one stage only. Because I have seen this. If I have seen this, picture is clear in my mind that what is happening. Half adder, producing sum being fed to the another half adder, produce the final sum. Here it is producing a carry and this second half adder is also producing a carry that is being owed and fed to the next stage. So, one stage I will draw and based on that I will be able to solve all the problems. So, this is how I will be solving in the examination. Okay, let's solve the next question which was asked in gate only. You solve it on your own, do not draw the full circuit. Okay, solve it on your own, write down your answer. I hope you must have solved it. The final answer is 12 nanosecond. So, if you are getting 12 nanosecond, that is correct. So, let's start. So, they started working at t equals to 0. Now, delay of my half adder will be equal to the XOR gate, that I know because picture is very clear, and OR gate, sorry, AND gate, that is 1.2 and this is having 1.2. So, these two guys started working at 0, 0. So, sum will be produced at 2.4. and carry will be produced at 1.2 nanosecond. This guy would be stable at 0 nanosecond only. So first circuit will start at, wait a second, sorry. So this guy would be stable at t equals to 0 only, but this guy is stable at 2.4 nanosecond. So first circuit will start at 2.4 nanosecond. So 2.4, some will take 2.4 more. So 2.4 plus 2.4, here I will be getting 4.8. And 2.4 plus 1.2, here I will be getting 2.4 plus 1.2, 3.6. And 3.6 plus 1.2, 4.8 nano. Right? Now I know that this will be fed back here. So now this 0 nano has become 4.8 nano. This 0 nano has become 4.8 nano. So this, in the next stage as well, this would have been already stable. So this guy would have been already stable and this guy would have been already stable. So this 2.4 nano is already there. So this guy will start working at 4.8 nanosecond. So 4.8 plus 2.4, because some will take 2.4 time more. So 7.2 nanosecond. At 7.2 nanosecond you are receiving your sum. And what about the carry? So 4.8 plus 1.2. So this will be stable at 6 nanosecond. 4.8 plus 1.2. 4.8 plus 1.2. So this will be stable at 6 nanosecond, and 6 plus 1.2, this will be stable at 7.2 nanosecond. Now it is again feedback. So 7.2 nanosecond. Now this guy started working at 7.2 nanosecond, right? This guy started working at 7.2 nanosecond. So 7.2 nanosecond it started working. So sum it will produce at 7.2 plus 2.4. That means 9.6 nanosecond. And what about the carry? 7.2 plus 1.2, that would be 8.4. So carry will be produced at 8.4 nanosecond. So wait, sorry. This carry will be produced here. This carry will be produced at 8.4 nanosecond, and 8.4 plus 1.2. So it will take 9 nanosecond. Are you getting this point? 8.4 plus 1.2, 8. This is 7.2, and 7.2 it will take 1.2 more time. So it would be generating the carry at 8.4. 8.4 plus 1.2 would be 9.6. So why I am writing 9? It would be 9.6 nano. Now this input will be stable at 9.6 nanosecond. So this guy will start working at 9.6 nanosecond, and 9.6 plus 2.4, what that would be? 9.6 plus 2.4, 12 nano. So this guy will be stable at 12 nano. And what about this 9.6 plus 1.2, that would be 10.2. So this guy will be stable at 10.2. 9.6 plus 1.2, that would be 10.8, sorry. So this guy will be stable at 10.8. Now 10.8 plus 1.2, that will be 12 nano. So your final sum and carry both are being stable at 12 nano. Just don't do the calculation mistake that the way I am doing. 9.6 plus 1.2, that is 10.8. But 10.8 this is stable, and 10.8 plus 1.2 this will be stable at 12 nanosecond. So your sum is stable at 12 nanosecond, and carry is also stable at 12 nanosecond. So what is the final answer? Final answer, or you should say maximum delay. So what is the maximum delay? That is equals to 12 nanosecond only. So this was our type 2. So for this type, I will give you a homework. Here there are 16 bit. So 16 cycles will come. But do you think you will solve all the cycle like that? No, you will see a pattern here. Here also we are getting a pattern. Can't you see 4.8, 7.2, 9.6, 12. 4.8, 7.2, 9.6, 12. So solve for few cycles, you will see a pattern there. That's it. So if you see the pattern, that would be your final answer. So you are not going to solve for the 16 bit. These kind of questions haven't been like these kind of questions, they never asked. They are asking for 4 bits only, so that guy can do this analysis. Or if someone is solving by this analysis as well, then also he will be able to tell the answer. But what if there are 16 bits? So you solve it on your own. The hint is you do not need to solve it completely. You will get some pattern there. Okay. So I will send the solution in Telegram group. You can join the Telegram group. And if you are watching this video carefully, if I mean something to you, if this channel means something to you, then you need to type your answer. Just type your answer in the comment section, so that I could know how much guys are understanding. So please type your answer in the comment section after solving this particular problem. So now we will move to the type third. We will pause for a while now, and now we will move to type third. So we will be back in some time. Hi everyone. So now we will see the third type of problem, and this is very important, and very high chance that if they are framing a question from full adder, then this kind of problems will come. So the problems I have written here, but before that I want to give you one very good concept that I have already given in our course, but let's see it here again. Okay, so this is the truth table of full adder, right? This is the carry and this is the sum. Mark that carry I have written first and then I have written sum. So if you talk about carry, then let's see these two lines. In these two lines, if my A and B are 0, if my A is equals to B is equals to 0, then without even caring about these two bits, I can directly say that my future carry would be 0 only. If my A and B are 0, then without even thinking of the previous carry, I can always say that my future carry will be 0. So if A and B are 0, then we will never care of the previous carry. We can directly give the output without even caring of the previous carry. If my A and B are 1, if my A and B are 1, then without even caring for the previous carry, I can always say that my carry will be 1 only, forward carry will be 1 only. Say yes or no? If A and B are 1, so without even looking back that whether my CI will be 0 or 1, we can always say that my forward carry will be 1 only. So if A and B are 1, so without even thinking a bit, we will always give CI plus 1 would be 1. So here there is no wait, right? No wait for CI. We are not waiting for CI here. No wait for CI. Right? Well and good. Do you agree to this point? But if A is equals to 0 and B is equals to 1, or B is equals to 1 and A is equals to 0, then your Ci plus 1 will be equals to Ci only. Basically, if A is 0 and B is 1, so let me take another color of pen, that is this. 0 or 1, 0, 1, 1, 0, 1, 0. So my Ci plus 1 is equals to Ci only. So here I will have to wait, because if A is 0 and B is 1, and if my Ci is 0, then Ci plus 1 will be 0. And if A is 0, B is 1, and if Ci is 1, then Ci plus 1 will be 1. So here my Ci plus 1 is not fixed. Ci plus 1 is depending on Ci, right? I can say that my Ci plus 1 is not fixed here, but it is a function of Ci, right? So here we will wait for Ci, wait for Ci to come. Is these 3 points are clear to you or not? See these carefully and see and tell me if these 3 points are clear to you or not. Clear? Because it will be very, very highly used. So if A is 0, B is 0, I am not waiting. A is 1, B is 1, I am not waiting. If A is 0 or B is 1, or if B is 1 or A is 0, I will wait for Ci. Let's see what kind of questions we are going to see here. So the type 1 we have already seen, no? It is the same kind of problem. Full adder is given, no internal structure is given, full adder is given, you need to find the maximum delay. Carry delay is given, some delay is given. But this time input are mentioned. Input are mentioned, that is 0, 1, 0, 0, 1, 1, 0, 0. And for t less than 0, all inputs were 0. So for t less than 0, all inputs were 0. So this carry would have been 0, sum would have been 0, this 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 would have been 0. Although you do not need to write it, you will be remembering it only, no? Basically, if previous bits were 0, so 0 plus 0 plus 0, all were added 0, 0, 0, 0, and carry would also have been 0. So everything was 0 for t less than 0. Now for t greater than 0, that means for that means at t equals to 0 plus, this has been applied. So here what all will be added? 0 and 0 will be added, 0 plus 0. 0 and 0 will be added, 0 plus 0. 1 and 1 will be added, 0 and 1 will be added, 0 and 1 will be added, right? Previous things were, all these were 0. Now and C naught is updated to 1, okay? C naught is updated to 1, and this happened at t equals to 0 only. Now all these inputs that we see here, all these are stable at t equals to 0 only, no? All these are stable at t equals to 0. Now I will go to this guy. What do I see? I see 0, 0. What do I see? I see 0, 0. I will ask him, do you wait for C naught? He will say, I don't wait for C naught. Although C naught comes at t equals to 0 in a second only, but he does not wait for C naught. He says that I do not wait for C naught. if you are applying 0 0 here, I can give my carry equals to 0. First I am talking about carry only. So now my updated carry is 0, which did not change. Previously also it was 0 only, now updated carry is also 0 only. So it will take 0 nanosecond time. Although let's just say if carry generated was 1, if carry would have been updated from 0 to 1, then it would take TC time, which is 20 nanosecond. So to generate the carry, it is actually taking 20 nanosecond time, but after 20 nanosecond you get to know that the carry is 0 itself. So it is stable at t equals to 0 nanosecond only. Now I will go to this guy. I will ask him, do you care of your previous carry? He will say, no, I do not care of my previous carry. So I can generate this carry immediately. It will take 20 nanosecond of time. To update from 0 to 0, it will take 20 nanosecond of time, but it is not even updated. If it was going from 0 to 1, then you would have said that it has been updated from 0 to 1 at 20 nanosecond, but it is not even updated. That means this is also a steady state at t equals to 0 nanosecond only. Is that clear? Let's go to this guy. What this guy will say? I will ask him, do you care about your previous carry? He will also say, I do not care, right? He says, don't care. He says, I also don't care. He says, I also don't care. Why it doesn't care? Because previous carry is, because A and B are 1. If A and B are 1, then it will always give 1 only, irrespective of whatever the bit there is. Basically, if this is my circuit and I have applied 1 1 here, so if I apply 0, still I will get carry 1. If I apply 1, still I will get carry 1 only. So it doesn't care whether it is 0 or 1. So just as you applied it at t equals to 0, at that time he said that I am gonna give carry 1. And to give the carry, how much time it will take? 20 nanosecond. Because here it is changing, no. Here also it was taking 20 nanosecond, but it did not even change. So we will say that it was always stable. Here also it was taking 20 nanosecond, but it did not even change. So we will say it was always stable. But here it is changing, so it took 20 nanosecond. So after 20 nanosecond, this bit will become 1. Okay. So this point is clear, no? If 1 1 is there, it doesn't care about the previous carry. If 0 0 is there, it doesn't care about the previous carry. Now I will go to the other guy. I will go to this guy. I will ask him, do you care about the previous carry? He will say, yes, I care about the previous carry. He cares. If he cares, that means he will start working when this is updated. So this will start working at 20 nanosecond. So this guy started working at 20 nanosecond. Say yes or no? Because he cares. Because for 0 1 0, your carry will be 0. But for 0 1 1, your carry is different. So he cares whatever that is behind him. So he cares about this carry. So they were updated at t equals to 0 only, but this bit was updated at t equals to 20 nanosecond. So this guy started working at 20 nanosecond. So now what will be the carry bit? 0 plus 1 plus 1. What that would be? 1 only. So this carry bit will be updated to 1. And how much time it would take? So this guy started working at 20 nanosecond, and to generate the carry, it will take 20 nanosecond more. So 20 nano plus 20 nano, 40 nano. So this bit was updated at 40 nanosecond. Did you understand this point or not? This guy said that I care about my previous output. I care about my previous carry. So if he is caring about previous carry, that means he will start working at 20 nanosecond. This we are talking about only carry. We will talk about sum now. Wait a second, we will talk about sum. So this guy said that I care about him. I care about the previous carry. So I will start working at 20 nanosecond only. When this guy comes, then only I will start working. So this guy came at 20 nanosecond and this guy started working. So to generate a carry, how much time it takes? 20 nanosecond more. So 20 plus 20, 40 nanosecond. So this bit is stable at 40 nanosecond. So this was about carry. Let's talk about sum now. So initially all the sum were 0, right? Now 0 plus 0 and this C0 is 1 here. So sum will be updated to 1. This guy came at 0 0. This guy also came at t equals to 0 nanosecond. So this complete adder started working at t equals to 0 nanosecond. If it started working at t equals to 0 nanosecond, that means it will give sum 1. And how much time it will take? What is the t sum? That is 10 nanosecond. So this will be stable at 10 nanosecond. Right? 0 0 0. Initially as well there was input was 0 and this carry was also 0. So initially sum was 0. After that as well, input is 0, carry is also 0. So this never got changed. So this was always stable. So this was stable at 0 nanosecond only. This never got changed. What about this guy? Initially 1 1 0 was there. Look, basically initial sum was 0. Then 1 1 was applied. Initial sum was 0. Then 1 1 was applied. If 1 1 was applied and this carry was 0, then what would have been the sum? When 1 1 applied, this was also there. This was at t equals to 0 nanosecond. This was at t equals to 0 nanosecond. This was at t equals to 0 nanosecond. This is the condition for t less than 0. Right? Now I am talking about t equals to 0 nanosecond because this was there at t equals to 0 nanosecond. So 1 1 0. What will be the sum? 1 only. Right? The sum will be 1. 1 1 0. Sorry. 1 1 0. Sum will be 0. Sum will be 0. Carry will be 1. So sum will be 0. After that as well, the carry never changed. Carry is always 0. So sum will also be always 0. So these are always 0 only. So it was always stable. The sum did not even change. Sum never changed. So it was always stable. What about this guy? When 0 1 0 was there, look, for t less than 0, what was the scene? For t less than 0, it was 0 only. At t equals to 0, what happened? At t equals to 0, this was 0, 1 and 0. Say yes or no? 0, 1 and 0 at t equals to 0. So at t equals to 0, the sum was 1. 0 plus 1 plus 0. The sum was 1. At t equals to 0, sum was 1. Sum was 1. Now after 20 nanosecond, this guy became 1. After 20 nanosecond, this guy became 1. So now the adder will say, I will add 0 plus 1 plus 1. So what is the sum of that? 0. So it will be updated to 0. When it will be updated, this guy started working at 20 nanosecond. And to get the sum, how much time you need? 20 plus 10. So t equals to 30 nanosecond. So it will be updated at t equals to 30 nanosecond. So this guy was updated at 0. This guy was updated at 0. This guy updated at 10 nanosecond. And this guy updated at 30 nanosecond. And this guy updated at 40 nanosecond. So your final sum came at 30 nano. And final carry came at 40 nano. So what is the maximum delay? 40 nano. And just wanted to add a point, like sometimes I have seen that people analyze some part wrong. Okay, they will analyze carry part correctly, but some part wrong. Like they do not even consider that initially there was 0. It might happen, like error may happen. Like from greatest of educators, the error may happen, but we need to analyze the carry as well. It's not that at that time it started working. So like I will show you a lot of example where the things will change in sum. So this was one of the example. I know you did not understand it 100%, but we will solve a lot of example. We will solve more examples. It will come to you again. Okay. So let's see the next example. The same question is there. 1 0 1 0 1 1 0 0 and C naught is 0. So C naught is 0. 0 will be added to 0 0 0. Sorry. 0 will be added to 0 0 0. 1 will be added to 0 1 0. Then 0 1 and then 1 1. So all the initial everything was 0. Initial everything was 0. Everything 0. Initial everything is 0. Now all these guys came at t equals to 0. All these guys came at t equals to 0. Right? This was also at t equals to 0. So this guy started working. For the first guy, you can directly see, okay, 0 0 0. I will ask him, do you care about the previous carry? He will say, no, I do not care about the previous carry. I will directly generate 0 here. So this guy did not even change. That means this was stable at 0 nanosecond. Now I will go to him and I will ask him, do you care about your previous carry? He will say, yes, I care about previous carry. So I will start working when my previous carry is stable. So my previous carry is stable at 0 nanosecond only. So this guy will start working at 0 nanosecond. 0 nanosecond, it will start working at 0 nanosecond. If it starts working at 0 nanosecond, what will be the carry it will generate? 1 plus 0 plus 0. It will generate 0 carry only. So if this carry is not even changing, that means it is stable at 0 nanosecond only. Now I will go to this guy. I will ask him, do you care about the previous carry? He will say, yes, I care about the previous carry. I will start working only when the previous carry is stable. So previous carry is stable at 0 nanosecond only. So he will start working. Now 0 1 0 is there. So how much carry he will produce? 0 carry only. He will produce 0 carry only. So this carry is stable at 0 nanosecond only. Now I will go to this guy. I will ask him, do you care about the previous carry? He will say, I don't care about the previous carry. I don't care about the previous carry. I will start working at t equals to 0 nanosecond. Even though if it is 1 or 0, I do not care about it. I will start working at t equals to 0 only. So I will generate output 1, carry output 1. Just as you apply the input, I will generate carry output 1 with the from here to here, coming from here to here. How much time it will take? 20 nanosecond. So it will take 20 nanosecond because my TC is 20 nano. TC is 20 nano. So this will be generated at 20 nanosecond. Let's talk about sum now. So initial bits were 0 0 0 0 only. After that also it is 0 0 0 only. So it got updated to 0 0 only. So it was stable at 0 nanosecond. What about this guy? Always 0 0 0. No bit change. Basically, sorry. So initially it was 0 0 0. So it was for t less than 0. It was 0. It was 0. It was also 0. So this was 0 only. For t greater than 0, at t equals to 0 nanosecond, it was applied 1. It was applied 0. And this was applied to 0 as well. So at 0 nanosecond, you got 1 0 0. So it will perform the summation. And what will be the summation? 1 plus 0 plus 0. That would be 1. And how much time it would take? It would take 10 nanosecond. Sum would take 10 nanosecond. Now you went here. So initial 0 0 was there, so sum was 0. At t equals to 0, you applied 0, 1, and at t equals to 0, your carry was 0 only. So it will perform the sum. And how it will perform the sum? It will make it 1. But how much time it will take? 10 nano. It started working at 0 nanosecond, so it will give the sum as 10 nano. What about this guy? When 0 0 was there, it was 0 only. But when 1 1 was applied, at that time as well, the sum was 0 only. Now 1 1 0 is applied, still the sum is 0 only. So sum never got changed. Sum never got changed. That means it was stable at 0 nanosecond only. So your carry was stable at 20 nanosecond and sum was stable at 10 nanosecond. So what is the maximum delay? 20 nanosecond. Well and good. Let's try solving the next question on your own. This is 0 written. In the back 0 is written. Okay, let's start now. So I will go to this guy 1 0. Do you care about the previous carry? He will say yes, I care about the previous carry, but previous carry is stable at t equals to 0 nanosecond only. And these guys are also, all these guys are stable at t equals to 0 nanosecond only. All these guys are stable at t equals to 0 nanosecond. So they will generate the sum. They will generate the sum, that is, forget about the sum. Sum we will see later on. And initial sum, all sum are 0. All bits are 0 0 0 0 0 0. Now I will now this guy will say that I care about the previous carry. If my previous carry is 0, my next updated carry will also be 0. But it was already at 0, so it would take 0 nanosecond time. All these carries are already at 0. So it would take 0 nanosecond time. Now you go to this 0 0 guy, you ask him, do you care about the previous one? He will say, no, I do not care about the previous one. I will give my next carry equals to 0. So if it is updated from 0 to 0, that means at 0 nanosecond it is stable only, right? Now I will go to 1 1. I will ask him, do you care? He will also say, I do not care. That means I will update my carry to 1 because 1 1 is there. So if 1 1 is there, he will update the carry to 1, right? Because if A and B are 1, my carry will always be 1. If A and B are 0, my carry will always be 0. So he also doesn't care about the previous carry. So he will say, I will update it to 1. And to generate this carry, how much time I will take? 20 nanosecond. For TC is 20 nanosecond, right? TC we have assumed to be 20 nanosecond. So he will say, I will take 20 nanosecond. Say yes or no. Now I go to this guy. I will ask him, do you care? He will say, yes, I care. Yes, I care. So I will generate my carry only when this guy is stable. So when this guy is stable at 20 nanosecond. So I will start working at 20 nanosecond. So this guy starts working at 20 nanosecond. So if this guy starts working at 20 nanosecond, that means now it will generate the carry. So what carry it will generate? 1 0 1. The updated carry here is 1. At 20 nanosecond, you see 1 here. So 1 plus 0 plus 1. What will be the carry? Carry will be 1. Carry will be 1. And if it is being updated, carry is being updated here. If it is being updated, that means it would take 20 already was there and 20 more time it would take. So 40 nanosecond it would be updated. Now I will ask him, do you care about the previous condition? Do you care about your previous carry? He will say, I do not care about the previous carry. So what do you think? It will start working at 40 nanosecond or it will start working at 0 nanosecond? It will start working at 0 nanosecond only. Say yes or no? Because it doesn't care about the previous carry. It doesn't care about the previous carry. Just as you applied 0 0, the full adder will not care about the previous carry. It will generate the forward carry immediately. So this has been stable at t equals to 0 nanosecond. Now I will go to him, do you care about the previous one? He will say I also do not care about the previous one. So here initial carry was 0. Now I do not care about the previous one and my carry would be 1. So this will be updated from 1 1. You started like this guy started working at t equals to 0 nanosecond. When this guy started working at t equals to 0 nanosecond, because it doesn't care about the previous carry. So if it is not caring about the previous carry, it started working at 0 0. So it generated carry equals to 1. So how much time it would take? 20 nanosecond, right? It would take 20 nanosecond. For carry, it would take 20 nanosecond. Now let's talk about sum. So initially 0 0 was there, so sum was 0. Now 1 0 1 1 0 0 is there, so sum has become 1 now. Sum has become 1. So to go from 0 to 1, how much time it would take? 20 nanosecond. Look, here it was the most important point in between, that this guy started working at t equals to 0 nanosecond only, because he knows that I do not care about the previous one. So even though this guy is being 1 at 14 nanosecond, but I don't care about that. Why I do not care? Because I am 0 0. So I will always give carry equals to 0 only, no matter what is my CI. So I do not care. So I will give my 0 at 0 nanosecond only. Although I should take time. I should take time of TC. To generate this carry, I should take time of TC. But this carry is not even being changed. So at 0 nanosecond only you will get the same answer. Right? So this you got at 20 nanosecond. What about this? Initial was 0 0. Updated carry is also 0. So nothing got changed. So this is stable at 0 nanosecond only. Here initial was 0 0. Then 1 1 came. If 1 1 came, that means it will take the sum to 0. If 1 1 came, it will take the sum to 0 only. Initially 0 0 and 0 was there. All three were added. So you got 0 only. Now it has become 1 1 0. So 1 plus 1 plus 0, the sum will be 0 only. Now after that, when carry came, it was again 1 plus 0 only. So this sum never got changed. This sum never got changed. What about this guy? So initial there was 0 0 0. So sum was 0. Then 1 0 0 was there. 1 0 0 was there, right? 1 was there, 0 was there. But this guy 1 came later on. At t equals to 0, I am telling. At t equals to 0. 1 was there, 0 was there, and this 0 was there. So at t equals to 0, this was 1 0 0. Right? So it would give the 1, it would give the sum 1. At how much time? It will take 10 nanosecond time. It will take 10 nanosecond. 1 0 0. It will take 10 nanosecond time. Now after 20 nanosecond, what happened? 1 was there, 0 was there, but this guy became 1. So after 20 nanosecond, he realized that my input are changed now. If my input are changed, so I need to do the action now. So what action I will do? I will change 1 plus 1 is 0 only. So I will again change. So at 20 nanosecond, it started working. To get the sum, how much time you require? 10 more. So 20 plus 10, 30 nanosecond. So this sum will be stable at 30 nanoseconds. So this was a very important point. Are you getting this point? Like I can guarantee you, no one will teach you this thing. Okay, like they are changing, how they are changing. So like we cannot say that it will start working at 20 nanosecond and then after 10 nanosecond more, this will be 0. Like if I had analyzed it in this manner, that initially this was 0. Okay, initially this was 0. Then after 20 nanosecond, it was 101. So what would be the summation? 101. Again summation would be 0. So I would feel like that the summation did not even change. But there is an intermediate state. There is an intermediate state at t equals to 0. At t equals to 0, this was 1, this was 0, and this was 0. So at intermediate state, in between, the sum got changed. So this is the waveform of sum. 0, then it became 1, then it became 0. So there was a change in state. So this will be the steady state. This is not the steady state. So the state of sum got changed here. So we always have to see for t less than 0, at t equals to 0, and if your carry is changing, after that what happens? So these three states we need to analyze when we are talking about the sum. Are you getting this point? Okay. So yeah. Now let's go to the next one. This is the toughest question which can, no, this is not the toughest, another part will come. Okay, this is not the toughest. So yeah. So let's analyze for this guy, for this carry. For this sum, sorry. So initial 0 0 was there, so this was 0 only. When bits got updated, this was 0, this was 0, and this was 0 only. At t equals to 0, this was 0, this was 0, and this was 0. At t equals to 0. So nothing got changed, it was 0 only. Sum was 0 at t equals to 0 nanosecond. It was going fine. suddenly at 40 nanoseconds this guy became 1. At 40 nanoseconds this guy became 1. So now what you need to do? 0 plus 0 plus 1. So now addition will be 1. So now you need to perform new addition, that would be 1. So it started at 40 nanosecond. To get here I would need 10 nanosecond more. So my answer would be 50 nanosecond. Okay. So my answer would be 50 nanosecond. Now here initial was 0 0 0, so sum was 0. Then at t equals to 0 nanosecond only 1 1 came. At t equals to 0 nanosecond 1 1 came. So my sum got updated to 0. After that as well, this carry was always 0. So it did not even change. It never changed. This carry never changed. So it also did not ever change. So it was always 0. So this was stable at 0 nanosecond. So which one is the latest one? Look, we always do not need to look at the final one. We always need to look which guy got stability latest. So this guy got stability latest. This guy got stability at 50 nanosecond. This guy at 30. This guy at 20. And this guy at 0 nanosecond only. And this bit was stable at 1 nanosecond. This so what is the maximum time? This is the maximum time. So maximum delay is 50 nanosecond. And if they ask you this question, that delay in getting C4, this is C4 or C5. Okay, there are much more blocks. This will generate C1, C2, C3, C4, C5. This is C6. So C6 got stable at 20 nanosecond. But this is not the maximum delay. Your final stable output you will receive after 50 nanosecond. Say yes or no. So is that concept clear to you? We have seen 3 examples. You have to pause the video and think on your own what is actually happening. Then only you will be able to understand. Get back to the video, rewind it again. You will understand a lot of new things. Okay. Let's go to this question. This is very conceptual and I have framed it on my own only. And you are not going to find these kind of questions anywhere that I can write on paper. Okay. Yeah. So just like telling that it has required a lot of efforts. So for t less than 0, a binary parallel adder will perform this kind of operation. For t less than 0, this operation is there. So 1 plus 1 is 0. 1 plus 1, this would be 1. 0, 0 and 1. Let me check if this is correct or not. 1, 0, 0, 0. So these are my steady state bits. Say yes or no. Steady state bits. Steady state. And these are my steady state carry bits. 1 plus 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. So here I am having the output 1, 0, 0, 1, 0. This is my steady state bits. And steady state carry bits are 1, 1, 1. Look, this operation has been performed for t less than 0. Although it was binary, although it was parallel addition, but here I did serial addition. Why so? Because I need the steady state. Let's say that I am solving a question of transient. So will I say that for t less than 0, will I say that my capacitor voltage charged to 5 volt? I will say that at t equals to 0, I will get 5 volt. That's it. So similarly, at t equals to 0, you will get these outputs, these outputs, and these bits, these carry bits. So here there would be 1, 1, 1. Now let's see what gets updated. So now these bits are updated, and they are not talking about C0. So C0 I will take 0 only. So now bits are updated as 1 0 0 1 1 1 0 1 0 1. Okay, ulta likh diya. Wait a second. So it would be 1 is added with 0, 1 is added with 0, then 0 is added with 1, 1 is added with 1, and 0 is added with 1. So now we will solve the problem. So here it was 0 initially. Okay, this guy came at t equals to 0. All these guys came at t equals to 0 nanosecond. All these guys came at t equals to 0 nanosecond. And this guy came at t equals to 0 nanosecond only. Okay, this should be given here. I forgot to write that that C0 is t equals to C0 is equals to 0 at t equals to 0 nanosecond. This should be given. Okay, now do you care about the previous guy? Yes, I care about the previous guy, but previous guy is 0 and it is starting at t equals to 0 nanosecond only. So if this guy is starting at t equals to 0, so now I can start my operation at t equals to 0 nanosecond only. So he will start the operation at t equals to 0 nanosecond and he will generate the carry bit equals to 0. Now the carry bit is changing. To generate this carry bit, how much time it took? TC time, which is 20 nanosecond. So this guy took 20 nanosecond time here to generate this particular carry. Although if 0 was here, so from 0 to 0 we would say that it is a steady state only, but here it got changed. So it was 1 1 1 1 1, then it got changed. So this would be the timing diagram of this bit. So it got changed at 20 nanosecond, right? From here it started working. To generate this carry, it would take 20 nanosecond of time. So it got updated at 20 nanosecond. Now I will go to this guy. Do you care? Yes, I care. So this guy got updated at 20 nanosecond. So I will start working at 20 nanosecond only. So this guy will start working at 20 nanosecond. So if this guy started working at 20 nanosecond, so now he will generate a carry. What that carry would be? Carry would be 0, right? 0 plus 1 plus 0. Carry would be 0. This guy started working at 20 nanosecond and it would take 20 nanosecond more time to update it. So how much time would be here? So this bit will be updated at 40 nanosecond. This bit will be updated at 40 nanosecond. Now I will go to this guy. I will ask him, do you care about the previous carry? He will say, I don't care about the previous carry. If you have applied 1 1, then I will start working at 0 nanosecond only. Because I don't care about the previous carry, I can generate my final output. I can generate my final C out, which will always be 1. So that I can generate. Now you will say that, sir, it would take 20 nanosecond of time. It would take, to update from 1 to 1, it would take 20 nanosecond of time, but it is always 1. So if it is always 1, that means it was always at steady state only. So I will call it, this is stable at 0 nanosecond only, because it never even changed. I will go to this guy. I will ask him, do you care about the previous one? He will say, yes, I care about the previous one. So now, what about the previous one? Previous one got stable at t equals to 0 nanosecond. So he will say that, yeah, now I can work at t equals to 0 nanosecond, because he is thinking for him. This guy is thinking here, but these guys do not care. These guys do not care about it. These guys do not care here. This guy is also caring, but this guy is not caring at all. Okay, this guy cares. It will start working at t equals to 0 nanosecond. If it started working at t equals to 0 nanosecond, what did he see? 0 1 1 1. So I will give my carry equals to 1. Now carry was already 1 only. So this did not even update. So the final carry you are getting at t equals to 0 nanosecond only. Final carry C4. This will be C1, C2, C3 and C4. C4 you got at t equals to 0 nanosecond. Final output means this is our final output. We have to look here. So this bit was always updated. Let's talk about sum now. So this guy started working at t equals to 0 nanosecond. Initially before that my sum was 0 by doing this calculation. Now if I do new calculation 1 0 0, my sum will be 1. So my sum got updated, and when this guy started working at t equals to 0 nanosecond, if this guy started working at t equals to 0 nanosecond, then how much time it would take to be 1? It would take 10 nanosecond more, because t sum is 10 nano, right? Now let's go here. Let's go to this guy. So initially it was 1, then it saw 0. When it was 0 1 1, then it was 1 only. Wait a second, where it was 1 1 1. Yeah, so at t equals to 0, what is the condition? At t equals to 0, for t less than 0, this is the scene. At t equals to 0, 0 1 1. So what will be the sum? 0. At t equals to 0, it shows 0 1 1. Sum will be 0. If sum is 0, then how much time it would take to come? 10 nanosecond, right? But at 20 nanosecond, it got to know that this carry has changed. At 20 nanosecond, it got to know that this guy has changed now. If this guy has changed at 20 nanosecond, then I have to give the changed output. What will be my changed output now? 0 plus 1 plus 0, and that would be 1. 0 plus 1 plus 0, that would be 1. So now my output will change. First it got changed here, now it got changed. Now it will change at how much time you will get it. At how much time you will get it. So it started working at 20 nanosecond, and how much time more it will take? 10 nanosecond more. So you will get it at 30 nanosecond. Let's see this again, okay? For t less than 0 or at t equals to 0 plus, you can say at t equals to 0 plus. At t equals to 0 plus, this was the condition, that it was 1. Then at t equals to 0, it got to know that 0 1 and 1 is applied. 0 1 and 1 is applied. Previously what was applied? Here you can say 1 1 1 was applied. If 1 1 1 was applied, it said that my some bit is 1. Now it got to know that 0 1 and 1 is applied. This happened at t equals to 0 nanosecond. This was there at t equals to 0 nanosecond, and this was also there at t equals to 0 nanosecond. Now it got to know that 0 1 1 is applied. Now if 0 1 1 is applied, it will say that my sum bit should be 0. So it will update the sum bit. Now how much time it will take to come here? 10 nanosecond. Now after 20 nanosecond, it got to know that now 0 1 0 is applied. So something got changed. So now my sum is also getting changed. The sum is being updated to 1. So it will say that my sum is updated to 1. So how much time it will take? 20 nanosecond more. So basically it started working at 20 nanoseconds. So it will take 10 nanosecond more. To generate the sum, you need 10 nanosecond more. So 20 plus 10, 30 nanosecond. So here you are getting the stable output at 30 nanosecond. What about this guy? So my initial here, this output 101 was there. So this was 0. At t equals to 0, what happened? This was 1. This is at t equals to 0. So at t equals to 0, this 1 came, this 1 came, and this was 1 only. So 1 plus 1 plus 1, it got to know that I have to update it. So it will be updated to 1. Now to update it, how much time it will take? It will take 10 nanosecond time. But at 40 nanosecond, it got to know that my input has changed. Input has become 110. So now if I perform the addition, what I will get? 0. So at 40 nanosecond, it got to know that. At 40 nanosecond, it got to know that my input has changed. So if input is changed and at 40 nanosecond, you got to know. So again, I will start working. Okay. At 40 nanosecond, it again started working, and how much time it will take more? 40 nanosecond it started working and 10 nanosecond delay. So it will take 50 nanosecond time. Okay. So this guy got updated at 50 nanosecond. Now here, previous bit was 110. So this was 0. At t equals to 0, what it got to know? At t equals to 0, it got to know that 011 is applied. At t equals to 0, it got to know that 011 is applied. If 011 is 011 is applied, that means I should update my bit to 0. I should update my bit to 0, which is already there. So it is at stable state. At 0, now this carry bit never got changed. Carry bit never changed. If carry bit never changed, that means 011 will always be there, and this sum will never change. So this sum never got changed. So what is the latest time where your stable output is there? That is 50 nanosecond. So my sum is stable at 50 nanosecond. Okay. So what is the final answer? That is 50 nanoseconds. Okay. So that's how we will solve these kind of problems. Now we are going to see the next concept, and for that you need to revise it completely. Spend more time, solve all the problems that I have solved again and again. See what is happening in the circuit. In the examination, if these kind of questions are coming, you need to perform it in this manner only. I have taken the toughest problem which can come, which is this. For t less than 0, they will make you analyze, and for t greater than 0, they will see what can happen. Okay then. Thank you. Not thank you very much. We will take another session. In this session only I will add that. So in that we will discuss the fourth type of problem, in which what we are going to do. What do you think? We will make this full adder using half adders and OR gate. So this is what we are going to do. Okay then. Yeah. So let's go to the fourth type of problems. We will take a pause and then we will come back. So now we will see the fourth type of problem. So in these kind of problems, full adder will be made of half adder and OR gate, and half adder will be made of XOR gate and AND gate. So internal structure is given. In the previous problem, internal structure was not given, inputs were given. So here inputs are also given and internal structure is also given. So everything is there. Now whatever that we have studied from the initial chapter, like delay of half adders and full adders, so from there to here everything will be used. Okay, every single thing will be used. Now they are asking output will be stable at what time. So these are the initial bits were 0, these are the updated bits, and at what time output will be stable. And this C0 is also becoming 1 at t equals to 0. So this has become 1 at t equals to 0 nanosecond. Okay. So first I will draw this block diagram, and then I will draw this diagram in my paper. Okay. And then I will start solving the problem. So one thing I know, that to this full adder, 1 and 1 is being fed and another 1 is being fed, and all are being fed at t equals to 0 nanosecond. So all are changing from 0 to 1. All are changing from 0 to 1, right, at 0 nanosecond only. And this guy is also changing from 0 to 1 at 0 nanosecond. Sorry, 0 to 1 nanosecond I wrote, 0 nanosecond. Okay. So now 1 XOR 1 will be 0 nanosecond. This will be updated at 0 nanosecond. And this is also updated at 0 nanosecond only. Right? This is 1. This guy is 1 here, which was updated at 0 nanosecond. And 1 XOR 1 is 0. But I will not say that 30 nanosecond time is taken. Why is that so? Because 0 did not even change. The 0 was constant. So this was updated at 0 nanosecond only. So now this guy is in action at 0 nanosecond only. This guy is in action at 0 nanosecond because both of the inputs are stable at 0 nanosecond itself. So this guy can give the output 1 after 30 nanosecond. So here output is changing. Output is going from 0 to 1. So after how much time? 30 nanosecond. Okay. Now one more thing I know. What do I know? That if my inputs are 1 1, then my Ci plus 1 will not depend on this Ci. So why do I need to look at this path? I will not even look at this path. Say yes or no. If my inputs are A and B are 1, then my Ci plus 1 doesn't depend on this Ci. So I will not even look at this path. I will go forward with this path only. Say yes or no. So 1 into 1, this was initially 0, this got updated to 1 at 20 nanosecond. So this got updated from 0 to 1 at 20 nanosecond. Now if it is becoming 1, then it doesn't need to wait for this guy. Say yes or no. Because this is a OR gate. This is a OR gate. So if this has become 1, that means this is 20 nanosecond. At 20 nanosecond this has become 1. No matter whenever it is coming, if the input of OR gate is 1, then it will give the output 1 only. So after this condition only, the OR gate has the capability of giving the output. So it will take 20 plus 10, 30 nanosecond time to give this output. So your carry is being generated at 30 nanosecond. And what will be the carry? Carry will be 1. I already know if 1 1 is applied, carry will be 1, or I can solve it as well, that carry will be 1. So at 30 nanosecond I am getting it. And what about this sum? Sum I am getting, that is 1 at 30 nanosecond. That also at 30 nanosecond. Okay. Now very interesting thing will come, like very interesting. All the shortcut method, everything fails here. That's the thing that will come here. So 1 0 1. So now this carry bit got updated from 0 to 1. For this adder we are talking now, 0 to 1 at 30 nanosecond, right? So 0 to 1 it got updated at 30 nanosecond. At 30 nanosecond. Okay. And now these bits are also different there. So everything I will clean up. In the examination you will have to cut it, right? There you cannot clean up. So this got updated from 0 to 1. One guy is from 0 to 0, one guy is from 0 to 1. This from 0 to 0 you can say, and this from 0 to 1. This from 0 to 0, this from 0 to 1. Why I am writing 0 to 0? That means initially it was 0 bit only, no? All bits were 0. So this transition happened at t equals to 0. So since this transition happened at t equals to 0, so these two guys will start working. Say yes or no? These two guys will start working at t equals to 0 only because they are stable at t equals to 0. So when it was 0 0, it was giving me 0 output, right? This was at 0 nanosecond. But when it is 0 1, it will give me 1 output. And this I will get at 30 nanosecond, right? So this input is becoming 1 at 30 nanosecond. And this input is becoming 1 at 30 nanosecond. What was your previous sum? That was 0. What is the new sum? Previous sum was 0. Why is that so? Why previous sum was 0? Because for t less than 30 nanosecond, this guy was 0 and this guy was also 0. Because it was becoming from 0 to 1 at 30 nanosecond. This guy became 1 at 30 nanosecond. So for t less than 0, this was also 0, this was also 0, sum was 0. Or you can say all the inputs were 0, so sum was 0 only. Now when it is updated 1 1, the sum is going to 0 only. Sum is already there. Are you getting this point? The best point of this particular program. The sum did not even change. So it feels like that delay should be 60 nanosecond, but nah, delay is 0 nanosecond. So here your final sum will be 0. So and that you will get at 0 nanosecond. Now one will have the doubt. What doubt some guy will have? That sir, for t less than 0, inputs were 0 0. So sum was 0. Okay, that I agree for t less than 0. But at t equals to 0 plus, what do I see? Sir, at t equals to 0 plus, I see that my inputs are 1 0 and here carry is 0. At t equals to 0, this was my carry. Carry is 0. So my sum should be 1. So sir, there is intermediate state. No, this would have been correct that there is intermediate state if this was a black box. But here there are two circuitry, no? So when these two guys changed, so it took 30 nanosecond time to become 1 here, and this guy also took 30 nanosecond time to become 1 here. So my sum did not even change. Let's just say if this delay was 20 nanosecond, if this delay was 20 nanosecond somehow, then in between this guy would have been 1 at 20 nanosecond and this guy would have been 0 at 20 nanosecond. So it would have changed its output. Then I could say that steady state, like in between there was another state, but there was no state in between. Are you getting this point or not? Both guys changed together. 0 was there, 0 was there for t less than 30 nanosecond, but both guys became 1 at 30 nanosecond. If this was 20 nanosecond, then there would be a scene that if this changed at 20 nanosecond and this guy is 0, so some would change its state, then at 30 nanosecond it will come back. Then you would say that 30 plus 30 at 60 nanosecond I have the steady state, but it is always remaining at 0. Say yes or no? So this intermediate state will not even come, because we are using two half adders there. Now this much depth will not come in the examination, okay? This much depth will not come. I just took blindly this particular example and this became very interesting. Okay, I blindly took it. And if the exam paper setter is also blindly setting, then it may happen that some good example may come up. So this guy became stable at t equals to 0 nanosecond. Okay. Now, so this guy is stable at 13 nanosecond, which is 1. And this guy is also stable at 13 nanosecond, which is 1. So now previously it was 0, but now it is changing its output. If it is changing its output, then it will wait for both of the guys, because it is an AND gate. So it will wait both of the guys. So from 0 to 1 it is going. At 30 nanosecond both are stable. So 30 plus 20, it will take 15 nanosecond of time. So this will become stable at 15 nanosecond. This became from 0 to 0 only. So this is 0 to 0. This goes from 0 to 0. So this was stable at 0 nanosecond only. But this became stable at 15 nanosecond. So this guy will have to wait for this guy. Why so? Because this is 0. And the output of OR gate is not defined with 0. For output of OR gate, you need 1. Or both 0 or both 1. But at least 1 you need if you want direct output. But direct output you are not getting. So this guy will have to wait for this guy. So this guy was waiting. After 15 nanosecond he came. So 50 plus 10. After 10 nanosecond you are getting this output. So 10 nanosecond this will be the output. And what will be the carry? You can do it, or you can directly know that it will be 1 only. Here also you can see 1 plus 0, it will be 1 only. So at 60 nanosecond it became 1. Say yes or no? Right? Now we will talk to the third guy. Okay, in the examination also, in gate examination also these kind of questions came, but that was pretty easy. That was pretty easy. Okay, and we will solve that particular problem, but there was not this much of concept involved. So you don't need to worry that sir, how we will solve in the examination. In the examination, how you will solve? When these kind of questions are coming, you will wait there that okay, something good is coming there. So you will get to know that this is a very good question. So I will wait there. I will not go blindly that let's solve this problem. So I will solve all other problems, then I will come back here. Okay, so these kind of problems just are there just to build your concept. Who knows what can be used anywhere? Let's just say they give only this circuit and they give the same input and they ask you at what time the output will be stable. Only this circuit, and the same thing they can say that A and B are changing at t equals to 30 nanosecond. Sorry, at t equals to 0, and Ci is changing at t equals to 30 nanosecond. What will be the time when output is stable? People will say 30 plus 30, 60 nanosecond. Output will be stable at 60 nanosecond. No, that is wrong. Output will be stable at 0 nanosecond only. Why is that so? Because output never changed. So these kind of concept can come up no in a short question. So that's why I deal a very big problem. I take all the cases so that you in the examination there is no need to worry about, right? So we are talking about the third one now. So one is changing to 0, another one is changing to. Now see this thing. Now do you think I need to solve this? No, carry is different, no. So yeah, I need to solve it. Otherwise, like if this was 30 nanosecond only, no. So I would not need to solve it. It was 60 or 50. 60 or 50. Here 30 plus 20, yeah, okay, 60 it was, okay. If it was 30 only, no, so I do not need to solve it because it would be the same. But here I need to solve it now. So this is 60 nanosecond. So this is changing from 0 to 1 at what time? 60 nanosecond. And one of the guys 0 to 1, same thing is there. 0 to 1, 0 to 1, no, 0 to 0. One guy is from 0 to 0 and one guy is from 0 to 1. Any guy could be anything, right? Because it doesn't matter. Now they will start their operation at t equals to 0 nanosecond only. So they would have started 1 XOR 0, this would become 1. This would become 1 at 30 nanosecond. Right? So for t less than 30 nanosecond, what would be the scene? For t less than 30 nanosecond, this was 0, this was 0, sum was 0. At t equals to 30 nanosecond, what is the scene? T equals to 30 nanosecond. This has become 1. This is 0 only because it will take 60 nanosecond of time. This has already become 1. So 1 XOR with 0. This is 1 at 30 nanosecond. Say yes or no? This is 1 and this will take 60 nanosecond of time to become 1. So it is already 0. 1 XOR 0, 1 at 30 nanosecond. Say yes or no? At 60 nanosecond, this guy became 1 and this is already 1 only. So 1 XOR 1, again 0. So at 60, sorry, this was at 30 nanosecond, no? This was 1 at 30 nanosecond. So 30 and 30 time it will take, no? So this will be 60 nanosecond. Really sorry. This will become 1 at 60 nanosecond. Why so? Because at 30 nanosecond, this was 1 and this was 0. So now it can start the operation, right? 1 XOR 0 will be 1, but to do the operation, it will take 30 nanosecond of time. So this will become 1 at 60 nanosecond. Now at 60 nanosecond, what is the scene? That this guy became 1 and this guy is already 1. So 1 XOR 1, it will again become 0. So this operation will start at 60 nanosecond. 1 XOR 1 will start at 60 nanosecond and you will get 0 after 60 plus 30, 90 nanosecond. So my sum is 0 only, but at 90 nanosecond. Say yes or no? What about carry? Carry will be 1, that I can directly see, right? Because 0, 1, 1, carry will be 1. But and why did I write 90 here? You go to know, because there is an intermediate state. In the previous case, there was no intermediate state. Now what is the scene? What we need to calculate? We need to see the path of carry. So carry. So for t less than 30 nanosecond, here there was 0, this was also 0, so this was 0 only, right? And then at 30 nanosecond, this was 1, but this was 0, this was 0 only. At 60 nanosecond, this is becoming 1 at 60 nanosecond. And this is also becoming 1 at 30 nanosecond. So at 60 nanosecond, both are 1. So now output will change. So after 60 nanosecond, output started getting changed. So how much time it will more take? 20 more. So it will be stable at 80 nanosecond. What about this? This will become, this was already 0 and already it is 0 only. So this will be stable at 0 nanosecond only. So after 80 nanosecond, this guy came here. That is 1. So 80 plus, so it will have to wait for this guy. So 80 plus 10, that is 1 you will get after 80 plus 10, 90 nanosecond. Right? So this carry you are getting after 90 nanosecond. Okay. Let's see the last condition, 1, 1. So in all other kind of problems, I gave you like some tips or tricks that there you can solve these kind of problems by that. But here I would want you to analyze it completely if these kind of questions are coming in the examination. I would not want you to do anything like make any random block diagram. In all the 3 cases, I told you how to do that in minimum time, right? But here, if these kind of questions are coming, I would want you to analyze there. Take your time. At least take 10 minutes. No one will like no need to worry about that. You need to draw the diagram, so you need to do everything there. Right. So now our C was initially 0, it is changing to 1. C is changing to 1 at 90 nanosecond. Changing to 1 at 90 nanosecond. Okay. And I will write down these inputs. I'm just wasting your time. I will write down these inputs. So this is the scene of our circuit. 0 to 1, 0 to 1, 0 to 1, 0 to 1 at 0 nanosecond, 0 to 1 at 90 nanosecond. Okay. So these guys will start working at t equals to 0. One thing I know, carry will not care about this path now, right? Because carry says that I do not depend on the previous carry now. So carry will forward this path. So it was initially 0, it will become 1 now. After how much time? 20 nanosecond. 20 nanosecond. So it will become 1 at 20 nanosecond. And it will be in action to give the output because this has become 1. So no matter after how much delay it is coming, but it will not care about this. So 20 plus 10, 30 nanosecond. So this will be 1 at 30 nanosecond. So this about carry, I know that this will be 1 at 30 nanosecond only, because this guy started working at t equals to 0 only. And if this guy started working at t equals to 0, this got changed, this got changed. This is 30 nanosecond, that's it. Now what is the scene about the sum? So that we need to check. So initially it was 0 here. Now again it will become 0 only. So it will be always stable. So this is at 0 only always. And for t less than 90 nanosecond, this was always 0. So sum was 0 only. But at 90 nanosecond, this is becoming 1. At 90 nanosecond, this is becoming 1. So 90 plus 30, 120 nanosecond. 90. So after 90 nanosecond, it will try to change. So 90 plus 30, at 120 nanosecond, it will change. So at 120 nanosecond, it will change. So this final carry you are getting at 30 nanosecond, this is you are getting, what is the maximum time? This is 90, this is 0 only, this is 30 only. So delay is 120 nanosecond. This question contains everything that can be there. Okay. This problem and this problem that is asked in GATE examination. These two you will solve, and every single case has been included. Whatever that can be a possibility, that has been included here. So look, these kind of information were given already. The circuit was also made. Okay. And input got changed 11000100, and this has become Z0 equals to 1. This has become 1, and these are the inputs. So initial condition were all 0 0 0 0. Everything was 0 0 0 0. Now if I go to the first one, I know that carry will not change, right? So now this guy can start working already. But like, let's solve it by the step only. Okay. Here I was just doing some smartness. What I was about to tell is that if 0 0 is there, this guy also did not change. So this will also give the sum 0. This will also give the sum 0. That means none of these changed. Only the sum here will change. So you just need to analyze this sum. Okay, just need to analyze this sum. If these guys are not even changing at 0 nanosecond, these are stable. No, this is also stable at 0 nanosecond itself. These guys did not even change. So just analyze this sum and then come here directly. That here you are having t equals 0 at 0 nanosecond. So these two blocks you do not even need to analyze. Only this block, for sum only you need to analyze. So for sum only I will analyze. So only C node got changed. Everything is same, only C node got changed. So here I will do it. So it is 0 only. It is also 0 only. This is also 0. This is also 0. So all are A XOR B. This is also 0. This is also 0 at 0 nanosecond. All these are at 0 nanosecond. But this guy got 1. This guy got 1 at 0 nanosecond. This guy got 1 at 0 nanosecond. This was already at 0. So before that it was 0. So your initial sum was 0. But now it will change to 1. So how much time it will take? 20 nanosecond. So it will take 20 nanosecond. Right? 20 is the delay, no? 20. Yeah. 20 is the delay. So this sum you will be getting at 20 nanosecond. These you are getting at 0 only because nothing got changed here. 0 0 0 was there, 0 0 is there. So everything is stable. So directly we are coming to the third stage. So this kind of easy question they asked. Okay. Here also I know that for carry I don't need to analyze much. Why so? Because I know carry will not see anything. Carry will go to 1. By which path? By the lower path. Because these are becoming 1 now. Na? These bits are becoming 1. So this is becoming 1 at t equals to 0. This is becoming 1 at t equals to 0. And this is also becoming 0 at, it will be at 0 only. So if I make the diagram for the third block, so how will I make it? Like it would be very easy to make in the examination. No? Like it is 0 to 0. 0 to 0 at 0 nanosecond. This is 0 to 1. All are becoming 1 at 0 nanosecond. So they will start their operation at 0 nanosecond itself. So if I talk about the carry, so carry will directly go here. That it will say that 1 1 is there, I will become 1 here. From 0 to 1 I will become at 15 nanosecond. And I do not care about this. I don't care about you. At 15 nanosecond I am there, so I have the capability of giving the output. So 15 plus 10 at 25 nanosecond I will give my carry 1 at 25 nanosecond. That's it. So directly this would become 0 to 1. 0 to 1 at 25 nanosecond. Okay. So last stage we will analyze, and for this we need to analyze the sum. So what will be the sum for this? 1 plus 1, it will be 0 only. So sum is also not changing na here. You can see, look, so this was there at 0 nanosecond, so this was stable at 0 nanosecond, right? And this will become 0 to 0 again. 0 0 was there, 1 1, 0 to 0 again 20 nanosecond, but it will not take 20 nanosecond, it will always be stable. So this guy was in action to give the output at 0 nanosecond itself. And what it will give? Initially it was 0, again it will give 0 only. There is no intermediate state. This guy was at 0 nanosecond, this guy was also at 0 nanosecond, this guy also at 0 nanosecond. So everything was 0. This guy got changed to 0 only. Okay, so nothing was, no change. Here no change. These guys changed. So we expected that there would be a change, but the change is same. So this was the steady state. This is the steady state. Now 0 0 will give you 0 only. So this was already a steady state, right? So sum you are receiving after 0 nanosecond. This you are receiving at 0 nanosecond itself. Already it is there. Now the final stage. What is the final stage? Now carry is becoming from 0 to 1. Carry is becoming from 0 to 1. Carry is becoming from 0 to 1. And inputs, one of the guy is 0 to 1 and one of the guy is 0 to 0. 0 to 1, 0 to 0. 0 to 1, 0 to 0. Okay, add 0 in a second. And this is becoming 0 to 1. At what time? This is becoming 0 to 1 at 25 nanosecond. So this is 25 nanosecond. Okay. So initially it was 0. Now it will become 1 at 20 nanosecond. At 20 nanosecond. Now see the very interesting thing here. So for t equals to 0, this all was 0, sum was 0. Now at t equals to 20 nanosecond, this guy is 1, this guy is 0. At t equals to 20 nanosecond, this guy is 1 and this guy is 0. So now this guy will say that I will generate 1, but it will take 20 nanosecond more time. That means it will be, you will get 1 here after 40 nanosecond, right? Say yes or no. This guy was 0. This guy was 0 here. Okay. So already it was 0. But 1 XOR 0 you are getting now. So 1 XOR 0 will be 1 after 20 nanosecond. So at 20 nanosecond you are having 1 here. And here you are having 1 at 25 nanosecond. That means it was 0 before that. It was 0 before that. Right. So here you are having at 20 nanosecond and it was 0 at 20 nanosecond. So 1 XOR 0, this will change. So at 40 nanosecond you will receive this. But what will happen is that at 25 nanosecond this guy will become 1. This guy will become 1 at 25 nanosecond. And this guy will be 1 at 20 nanosecond. So after 25 nanosecond, this guy will say that after 25 nanosecond, this XOR gate will say that 1 XOR 1 I will give 0. So after 25 nanosecond, it started the process of giving 0. Look, the thing is 1 was going, but behind that 0 also started coming. 1 was going, it said that it will take me 20 nanosecond more. So 20 plus 20 I will reach there at 40 nanosecond. And this guy is saying that I will be 0 after 20 like 25 nanosecond I started at 25 nanosecond and I will be 0 at 20 nanosecond more, after 20 nanosecond more. So I will be there at 45 nanosecond. So this will be there at 45 nanosecond. Are you getting this point? In between there is a state. So state is changing. So you will say that the output is going from 0 to 0, but it will take time. What is that? 45 nanosecond. Are you getting this point or not? Like I have seen this solution a lot at a lot of places, but nobody analyzed this condition. Luckily they got the correct answer. They are saying that this is being stable at 25, this is being stable at 20. So this will pick the maximum, 25 plus 20, 45. But there is an intermediate state. If it is going from 0 to 0, then why are you saying that it is changing? You can say no, it is already at steady state. Why you are not saying that it is at steady state? It is changing there. Why it is changing? In between at 20 nanosecond the things are different, 1 and 0. So at 40, 1 and 0 is there. So at 40 nanosecond it will become 1 and then again it will become 0. Okay, so in the last only there was a twist. Okay, let's talk about this one, this carry. So our carry will care about everyone now because it is 1 0. So if it is 1 0, this will go from 0 to 0 only at 0 nanosecond itself. Now let's talk here. So this will become 0 to 1 at 20 nanosecond, and this will become 0 to 1 at 25 nanosecond, right? 20 and 25. Now for t equals to 20 nanosecond, this is 1, this is 0. So output is 0 only. When output will change? When both are 1. When both are 1, then only output will change. And when both are 1? At 25 nanosecond. So at 25 nanosecond, this guy will start working and it will say that I will change my output to 1. At what time? 40 nanosecond. So this guy is there at 40 nanosecond. So 40 plus 10, this guy will become 1 at 50 nanosecond. So this carry will be generated, that is go from 0 to 1 at 50 nanosecond. So that's the actual solution. You can send it to anyone, anywhere. That's the actual solution with all the analysis of intermediate state of this particular problem. And this is also a very good problem where things got changed. Some was getting changed. No, but it was not taking a time. Here some was getting changed. Still it is taking 19 nanosecond time. Okay. So this is the complete analysis. I hope you must have understood all kind of delay problems. Apart from this, nothing can be asked. They are not going to ask anything apart from this. So this was one of the topic that I wanted to deal in a very good manner. Always I wanted to deal it. So yeah, that's it from my side. I hope you enjoyed it. If you enjoyed it, just like I would need your comment here. At least I would need one of your comment. So that would make me feel good. Like if someone is writing something good about me, it makes me feel very good. If I am working 12 hours a day, I will work 14 hours a day. If you write something good. So that's the thing I would be expecting from you. Okay. So yeah, thank you very much. Happy learning.